Thank you all for coming so early in the morning to hear more about the story of HiGHS. I've come from Edinburgh in the Edinburgh Research Group of Optimization in the School of Mathematics, University of Edinburgh. So we are mathematicians, but this talk will have very little maths in it. As exciting as the technical details are, I've kept them to a minimum. So let's jump. Oh, like here? Sorry, is this okay? Okay, I'm not going to move too much. So let's jump into the overview. We'll start with some minimal background on what problems we solve, and then I'll spend a bit more time on the history of HiGHS and the original contributors. Then I'll talk a bit about building HiGHS from the ground up. Then we'll go on to programming languages and interfaces that we support. We'll talk a bit about our users. I'll introduce the team. And towards the end, I'll spend a bit more time on our current work and our plans for the near future. Starting with some background, most of you here will know what an LP is, but just in case someone's not encountered LPs before, I will introduce the problem. The classic way it's taught to undergraduates is with the diet problem. So imagine you're a student and you're in the supermarket and you want to save money and you need to buy food. The problem is, given the cost of food items, what should you buy to satisfy your nutritional requirements and spend the least money? Mathematically, this can be modeled with unknown variables x for the decisions that we'll make. The decision quality is measured with the linear objective. The nutrient requirements can be captured with the constraints, and we can force realistic decision with the bounds on the x variables. What is HiGHS? HiGHS is open source software for large-scale sparse linear optimization. And as Matthew pointed out, the I in HiGHS is my name, and these are the names of the original contributors: Julian Hall, myself, Chi Huang Fu, and Lucas Shork. You'll see more details about them in the slides to follow. So this is an LP's formulation mathematically, but we can do more. If we add integrality constraints to the LP, we get a mixed integer programming problem. And if we add a quadratic objective to the LP, we get a QP, quadratic programming problem. So these are the three types of problems that we can handle. So HiGHS features a simplex interior point and first order method solvers for LP, a branch and cut solver for MIP, and an active set solver for QP, and it's written in C++. It's freely available on GitHub under the MIT license. We have no third-party code in HiGHS yet. There are interfaces to other languages and systems, and we have a nice website that you can check out if you want, called HiGHS.dev. HiGHS is the world's best open source linear optimization software, as demonstrated in the Mittelman benchmarks from 2022 onwards. And this was my short introduction. And I'll continue to the history section, where I will tell you some background about the original developers, how the project was created initially, and I'll introduce the person who created our MIP solver. It all starts with Julian Hall, who has been in Edinburgh since 1992 until today. Julian developed a primal simplex solver in the 90s, and that is important in this talk, so I've put it on the top. He had 2 attempts to parallelize the simplex method in the 90s, but they were not so successful because they were done on non-deterministic machines, and it was all very difficult for Julian and Ken. In 1999, Julian, Hall, and Ken McKinnon together identified the phenomenon of hypersparsity. More LP work is a scalable parallel simplex solver for stochastic LPs in 2012. That was work done with Miles Lubin. And Julian has done consultancy work since 1997. So one important project of his I will talk about next. The animal feed formulation problem is much like the human diet problem. Animal feed is blended from many ingredients, and there are multiple animals and multiple diets, and there are shared materials, and we need to formulate the solution at minimum cost. And this problem has a Danzig-Wolff structure, where the matrix has block angular structure, which is found in certain large-scale LPs, and they are independent blocks of constraints linked by linking constraints in the column or row. And there is one company that Julian did work with called Format Solutions. That was in the 90s. Their software still, I think, blends half of the world's manufactured animal food. For a reference, the farm food is in the order of billions of dollars. The pet food is in the order of tens of billions of dollars in revenue, and they trade the commodities as well. And they started using Julian's solver MSOL in 1998. Related to this project, there was an impact case study in 2021. Now, many of you will not know what an ICS or a ref is, and I will explain later in the talk why this is important. And MSOL was written in Fortran 77 by Julian in the 90s because that is what he knew. Now we'll go to the second very important person in the HiGHS history. That's Chi Huang Fu. He did his PhD in Edinburgh from 2009 until 2013, and it was partly funded by Format International, the company from the previous slide. So for his PhD, Chi developed a parallel dual simplex solver called HSOL. It was really good, and with Julian, they won best paper prizes from, I think, 3 different journals, and 2 of them are computational optimization and applications and mathematical programming computation. Chi finished his PhD and left Edinburgh and left Julian the C++ code. Later on, he went to FICO and made Express the best simplex solver in the world, and afterwards, he joined Cardinal Operations, which is a large Chinese company with currently the best solver from China. We've got one more person here, that's Lucas Shork. Lucas did a PhD in Edinburgh with Jacek Gonzio on interior points, and Jacek and Julian are in the same research group. Jacek was my second supervisor as well, so that was nice. They developed a basis preconditioned interior point method where the Newton system is solved by preconditioned conjugate gradient. And the preconditioner is derived from a weighted simplex-like basis. When Lucas left Edinburgh, he left Jacek, his supervisor, the C++ code of IPX, his solver. Later on, he joined Cardinal Operations as well and developed their interior point solver. Now back to Format Solutions in 2016. Julian had the C++ code for 3 years, but couldn't do anything with it because he didn't know C++. And then I came and I just started my PhD and I knew a bit of C++. For my master's project, I wrote a pre-solve for LP implementation and combined the pre-solve with HSOL, the simplex code. And we made some experiments for format solutions. There is something else here to mention. Julian was still supporting format solutions, but he was not convinced he could do anything with MSOL anymore because it was a Fortran code that he hadn't touched in 20 years because he didn't have to. It worked, but he wanted to feel better about being able to support his code. So he thought it would be nice if we could use HiGHS and HSOL instead. And HSOL alone was 2.5 times faster. And with pre-solve, it was 9 times faster. So format were really impressed, and they gave us some money to continue development of what was to become HiGHS. Now, implementing pre-solve for me was really fun. I really enjoyed it. It's a great set of tricks. And here I have an example of how beneficial pre-solve could be for a problem with 30,000 rows. It can easily reduce it to a problem with 13,000 rows and reduce the non-zeros by half. And that's just a very basic set of pre-solve rules. So that's a bit more on me. For myself, I can say I was just at the right place at the right time. I interned at Google in 2018, which was really nice. Actually, here in Paris, in the OR team, I'm in charge of the maintenance and of build and testing of HiGHS. I'm employed by the School of Maths from 2022 onwards, which was just when I finished my 7-year PhD with Julian, half of which I spent on HiGHS. And in 2018, we had pre-solve, the dual simplex solver, the interior point solver, and the name HiGHS is thanks to Matthias Miltenberger from SUSE Institute Berlin. We were visiting and brainstorming for names, and he came up with this idea. The final person I want to introduce in this section is our real superstar, Leona Gottwald. She joined us in 2020 for 2 years. She was at SUSE Institute Berlin before, working on Skip. She'd done a few years of programming and had some ideas about how to improve Skip, but they were hard to implement in the Skip context. So Leona joined us and we gave her the opportunity to write a MIP solver from scratch, and she had a lot of work with Julian, and Julian was tweaking the simplex solver as Leona wished the whole time. Sometimes he said he felt he worked for her rather than the other way around. It has been the world's best open source MIP solver since 2021. This is a snap of Mittelmann's benchmarks. COPT is the Chinese solver in red. It's red because it's closed source, and the blue ones are open source. There is actually one other solver that should be on the top, but it's called Groby. It's a US solver, and they dropped out of the benchmark some years ago because of some drama that I didn't really understand. But anyway, that's why we compare to COPT now, and HiGHS from the open source solvers performs best. Skip is a little while behind, but it's a bit hard to improve Skip much with their configuration. And CBC and GLPK are lagging a bit behind. There are question marks because these results are from a previous version of the benchmarks. Hans Mittelmann decided to drop them from the benchmarks because they time out too much. So they may be slightly better if he's got a faster machine now. And that was my brief history of HiGHS. So I will talk a bit about how we transformed HiGHS from gradware, which is what people code, the code their students leave them when they leave, into software. So what we had at the start was a computer program written and used by a single very talented person. These were Chi and Lucas. And we needed a well-maintained product used by multiple people. And that's not so easy. And it can be very important to avoid mistakes early on. That will get you in trouble later on. There was one book that greatly inspired me, and I recommend it if you're interested. It's called The Mythical Man Month by Frederick Brooks. He is best known for managing some development in IBM that was on a large scale. And in his book, he introduces this idea of conceptual integrity. It all sounds very simple and nice in theory. Examples are to maintain a unified structure as new features are added to the code, to avoid future inconsistencies, to have a well-defined execution of the program, and to avoid duplication or broken code or outdated code. And this sounds simple and intuitive, however, is rarely followed. And the reason is that keeping things simple is very time-consuming. There's a lot of cleanup involved. And that's one of the reasons many tech startups fail. Now, HiGHS is not a startup, but managing it has felt a bit like managing a startup. So what happens generally in new companies is that when it starts to take a lot of time to fix minor problems, companies hire more people. And then the overhead of managing the work between these people becomes a lot of work, so it all blows out of proportion and things crash. Now we don't have that problem. But just to quantify the resource estimations, Frederick Brooks introduces the following concept. There's a program, which is the code with its functionality. There's a programming product, which is the code, any tools for testing the code, documentation, and the build infrastructure. And there's also a systems program, which is the code, along with any interfaces and links to integrate it within other systems. So, in terms of man-hours, the estimation is that transforming a program into a product takes 3 times the amount of resources. So adding tools for testing, documentation, and build infrastructure. And then transforming a program into a systems program also takes 3 times the resources. So a programming systems product takes 9 times the resources compared to the original program. And what does that mean for HiGHS? We had to do generalization, documentation, and testing. And starting from the simplex solver, we added pre-solve, interior point, a primal simplex solver, which was also developed by Chi Huang Fu when he came back to Edinburgh for a master's after he already had a PhD and worked in FICO. The QP solver was written by Michael Feldmeyer during his PhD in our group. And the MIP solver, so this is the generalization part. And on the system side, we developed our build systems, we bug fixed for all the operating systems, we made HiGHS work with different compilers, programming languages, interfaces, and package managers. And this was a lot of work, and we had a lot of help. So thank you to everyone who has helped us along the way. I'm not going to bore you too much with the build system details, but we use CMake. We have used CMake from the start. Actually, Matthias Miltenberger, who came up with the name, also laid the foundations of the HiGHS CMake. We support Bazel for our tools, and we support Meson for Meson-based projects. I took the liberty of copying the results of a Reddit poll from 2020 because I was curious what people's favorite build system is. And CMake seemed to be the most popular at the time. I think the other section would be bigger now because Meson's gained popularity. But overall, people were not super happy about any. We've decided to stick with CMake. It gets updated often. There were CMake and modern CMake and more modern CMake and now even more modern versions. We are managing to keep up. It's not so easy. We support older versions still. It may be the best we've got so far. We will explore Meson further probably. I had a not so great experience with Meson, but we'll see how that gets on. So that was all I wanted to share on the build, and now moving on to programming languages and interfaces. The officially maintained ones by us are C++, C, Fortran, Python, and C#. And the ones below are developed by users, and they're not yet officially maintained by our team. That's Rust, JavaScript, and R. Rust has a little star on it because I am now an official maintainer of the Rust interface, but I've not had so much time to look at it yet. With HiGHS, we really wanted to put the time and effort in to make it easy to use for people with different skills from different backgrounds. And we wanted it to be useful for experienced modelers as well as industry people who don't really have so much programming background or knowledge. And we wanted HiGHS to be easy to use, even if you don't know the algorithms and maths behind it as well. Some more interfaces. There's the star jump on the top. There's more on jump coming on the next slide. It's very well used, and many thanks to Oscar Dawson, who's in charge of jump. We've got GAMS. Another thank you to Stefan Wigierski from SUS Institute Berlin, who has been helping us greatly from the start with all sorts of exotic stuff. We have an Ample interface, thanks to the Ample team. And the latest addition to our set of major industrial users is MATLAB. We have been the default solver in MATLAB since the spring this year. We have active contributions from their employee Franz Wesselmann and the PhD project coming up, which I'll talk about later on. Now we're at the Julia conference, so let's talk about Julia a bit more. There's JUMP. It's a modeling language and collection of supporting packages for mathematical optimization in Julia. We have been friends for a long time. Oscar Dawson has helped us a lot, including with the HiGHS documentation, which is built with Documenter.jl. There's the Julia wrapper, HiGHS.jl, the JUMP package, and we have been doing a recent collaboration on a large project to support open source energy modeling. There's a bit more on that later on. And just overall, JUMP's management and support and website and annual meeting have greatly inspired HiGHS, and we've modeled our website and annual meeting after JUMP's. Some packages where HiGHS is available. There's a HiSpy on PyPy. We have a C#, like a .NET package on NuGet. We're on VC packages, that's Microsoft Package Manager. We're on Conan, Homebrew for Mac, Bazel. Conda Forge has two because HiGHS and HiSpy are separate there. That may change in the future. Maybe there will be one. We have a Crate for Rust. We're on Nix for Nix OS. And SciPy, we have been the default in SciPy for a while now, but there's a star because they're using a really outdated version of HiGHS. And they're in the middle of a large refactoring to allow them to easily update to new versions, but that's a work in progress. So just something to keep in mind. Some work in progress. We need a bit more on OR tools. There is an interface thanks to the Google team, it's very good, but it needs to be extended further, and that's some work for me. I have some tests to work on. I need to look at Rust when I get the time. JavaScript is next. C# needs a bit more work. I need to thank Markus Ludwig Vermer and his colleagues from Menz GmbH. They contributed the foundation of the NuGet package and have been helping us with support. We are working on callbacks at the moment with a contribution from another user of HiGHS. People have asked for callbacks in .NET for quite a while now. It's far from perfect, but we are trying to catch up propagating new features. In my perfect world, when we have a feature, it will appear everywhere instantly, but that's not been as easy as I was hoping. So I'll talk a bit about HiGHS use cases. We are the open source default in many interfaces now, including Jump, SciPy, Pyomo, Ample, GAMS, and R. We've got some reasonable commercial use from large companies like MathWorks, Tesco, Microsoft Research, and Kraken. Tesco is a large UK supermarket chain, and Kraken is a UK energy utility company. They were originally part of Octopus Energy, but they have branched out and become independent some time ago. It's hard to know how many people are using HiGHS. We estimate at least thousands of industrial users, and many, many more if we include the customers of our customers. These are our best estimations. The PyPy package has 400,000 downloads a month, and the NuGet package has 18,000 downloads a month, and we have no idea how many of these are real, so we can't really know how many users we've got. But I have a couple of weeks ago started to assemble a list of HiGHS users for our website. So I got in touch with some of the people who subscribe to our newsletter and asked if they wanted to be added to the list. And this is what I got so far. Well, some of them we knew about before, like Edinburgh Airport. Use cases include resource allocation, scheduling, logistics, public transport, finance, consulting. And lately, HiGHS has been used more in the energy industry. So some of these companies do power system optimization, water management, energy equipment, renewables, and so on. And I will proceed with some more notes on energy modeling. We have had major funding from Breakthrough Energy to support open source energy modeling, and it has allowed us to hire a new MIP developer to work on our MIP solver. We didn't have a MIP developer since Leona left us in 2022. We have been doing joint work with Jump to improve support for energy modelers, and this last bit I took from Jump's website. It's used to build continental scale energy system models, including MIT's GenX, NREL Sienna, SpineOpt, and TNO's Tulipa energy model. And there is actually a talk on Tulipa energy model later today, so I hope you attend that and you find that interesting as well. This was my user overview, and now on to the team overview. There's Julian Hall, the man himself, founder, runs the show. Myself, in charge of build systems. We have Filippo Zanetti, who is the developer of our new interior point solver. I will talk about this more in a little bit. We have Yanyu Zhou. She's a student working on first order methods for LP. We've got Ben Champion, who's a student working on mixed integer problems for the benefit of Kraken, the energy group from the company from the previous slide, and Mark Turner, our latest addition as our new MIP developer. The team size has doubled over the past year. In the previous years, there was always 2 or 3 of us, and we are now 6. So that's really great that we have people to actively work on the solvers. And the great question is, how do we fund all of this? So I'll talk a bit about funding sources. Initially, we thought that we could do consultancy contracts, as people have done in the past. And the first major one allowed us to hire Leona and fund the development of the MIP solver. So that was nice, but a major drawback to keeping developers is offering them only short-term contracts. So we couldn't offer Leona a secure longer-term position, and she left and went to FICO Express. We have had charitable donations from small and large companies. We have platforms on GitHub sponsors and a donation thing on the Linux Foundation page. But what really matters are the large chunks of money. So we got a $420,000 donation from Google. They had a sustainability initiative, and that allowed us to hire Filippo and fund Janu's PhD. I'll talk about this more in a bit. Our current funding sources are Breakthrough Energy. We got $600,000 between HiGHS and JUMP to support open source energy modeling, and that allowed us to hire Mark to work on MIP. We've got funding by Kraken, who fund Ben's PhD, and MathWorks. MathWorks contribute the time of Franz Wesselmann. He was supporting their LP solver before, and now that they're using our solver, he's got time to help us, and it's in their interest. He does bug fixes. He works on pre-solve and on MIP as well. And this is all nice because this year, from 0 MIP developers, we went to 2.5 MIP developers. And that's really great because we needed someone to be able to maintain the solver that Leona left us. And we lacked MIP expertise in the team. And we've got an upcoming PhD with MathWorks. Some challenges. Companies do not generally pay for support because HiGHS is free and open source, and they just take it and use it and it works, so that's all fine. We can't really get academic funding because our research output would be too low. There's nothing novel in what we do. Maybe the odd bit somewhere, like there will be a paper on Filippo's interior point solver, but in terms of numbers of papers that we could produce, they wouldn't be enough. And we don't really want to play the game where we spend a lot of time on writing papers that could be spent on writing code. So we're not certain about funding long-term, and it's also quite hard to find developers in our area. In areas like MIP and interior point methods, there are very few skilled people, and the commercial solvers sort of fight each other over acquiring them as early as possible when they graduate. And it's difficult to the following extent. Gurobi is the largest US commercial solver for MIP, and recently they launched a 2-year MIP developer training program where they will train people on MIP so the trainees could work on Gurobi's MIP solver. And 2 years is a significant investment of time and money. Our hope in HiGHS is to be able to generate enough funds to keep our people. One important note and final about funding is this impact case study business in the UK. So REF stands for the Research Excellence Framework. And they do a periodic assessment of the quality of research in the UK. That happens every 8 years via case studies. And the results are used by funding bodies to allocate public research funds. So a great portion of the research funding of the School of Mathematics depends on being able to demonstrate that the research translates into socio-economic impact. And HiGHS is one of few impactful activities in the School of Mathematics. A top-class case study like Julian's in 2021 that I mentioned at the start of the talk, the one with format solutions, is worth $250,000 per year to the School of Maths because of their large business quantities. And it's important for us to demonstrate the valued use of HiGHS in the industry. I got my job thanks to this impact funding. And Julian is allowed to teach a bit less and have lower administration requirements because of this impact funding. So if we want to continue to be tolerated by the school, we have to generate some money for the school. Letters for the next impact won't be needed until mid-2027, but we have to show that we have offers of letters before that. So if you have a company that uses HiGHS, please consider acknowledging that publicly. It has been surprisingly difficult to get people to write letters for us. And that was all on funding. Now to the really exciting bits, our current work. The first next step I will like to talk about is HiPol. That's Filippo Zanetti's new interior point solver. It's pretty much done. We're already integrating it in HiGHS. It will be released soon. That means probably in our next release. It's got dependencies, which is bad news for me, but we'll do our best at managing them. It depends on BLAS, Metis, and GKlib, because Metis depends on GKlib. It will be available in C++ and Jump first. It will take various amounts of time to go into the other interfaces. And why did we need a new interior point solver? I don't know if you're familiar with PIPSA. It's an open source energy system modeling project. And they have data and models. And they needed an efficient LP solver. So some experiments were performed comparing with Gurobi. And the results were that CBC and GLPK, the other open source solvers, were uncompetitive even on modest instances. HiGHS was 10 times slower than Gurobi, and HiGHS was uncompetitive on large instances. So these results led to Google's donation to develop a parallel interior point solver for HiGHS. And why couldn't we just parallelize our existing solver, as demonstrated on the next slide? It's because of the nature of the solution method for the interior point algorithm. The current solver that we've got, IPX by Lucas Shork, is an iterative solver, and it solves the normal equations using a Krylov method with a basis preconditioner. And the new solver is a direct solver, which solves the augmented system or normal equations using its own LDLT factorization. And because of the different nature of algorithms, they have very different qualities as well. Particularly, IPX is serial and cannot be obviously parallelized. It's got unpredictable running time. It cannot be used for QP, but it's got a very low memory usage, a very high accuracy, and very good performance on some problems. In contrast, the new solver Hypo is parallel, has predictable running time, can be used for QP, but it's got a higher memory usage and it may fail to reach the same accuracy as IPX. However, it performs very much faster on many problems, some of which were these energy system models. First order methods, now GPUs are all the hype, and PDLP has become super popular since it came out a few years ago. HiGHS already has a CU-PDLP-C version integrated with support for NVIDIA GPUs, but we've got some funding from the UK National Energy System Operator to develop our own PDLP solver for HiGHS. That will be in C++ and later CUDA. We've got Yanyu Zhou working on first-order methods for her PhD. She will study extreme scale LP solution. And we plan to support other GPUs in the future. GPUs into interfaces will take an undefined amount of time. More of the exciting stuff. MIP. Mark Turner has got some work in progress already. He joined us in May this year. He brings invaluable MIP expertise to the team. He's got degrees from Australia and a PhD supervised by Thorsten Koch at ZIB. Mark's already working on parallelizing the dive in the branch and bound tree, parallelizing the heuristics later on, new tricks, and generally we would like to have better support for open source MinLP projects. Since Leona left us in 2022, very little has been done on the MIP solver, but what we have so far in terms of improvements are the ZI rounding and shifting MIP primal heuristic added by Franz Wesselmann. We've got the feasibility jump heuristic added by Ben Champion. We've got tightened CMIR cuts by Van der Hulst, and implied bound separator is corrected or strengthened by Mark this year. And that was on MIP. Going forward to QP, we've got a PhD coming up funded by MathWorks starting in January 2026. The plan is to have a project to enhance the QP capabilities of HiGHS. We would like to extend the active set solver to find local solutions of non-convex problems. And it will be necessary to extend our new interior point solver to QPs as well. And we were thinking possibly there could be a research scope in first-order methods for QP. We would like to support open source MinLP projects, and Giovanni Ghisalberti will join us in January 2026. He's got a bachelor's in aerospace engineering and a master's in mathematics from the Netherlands. We met at the HiGHS workshop this summer. If you would like to find out more, we have a newsletter, no more than 2 or 3 editions per year, so we're not going to spam your inbox too much. You could sign up on highs.dev. We have the workshop. We've already had 2 annual meetings, and the next one is next year, just before SIAM optimization in Edinburgh. SIAM optimization starts on the 2nd of June, so it's likely the HiGHS workshop will be on the 1st of June, and it will be done simultaneously with Jump Dev in Edinburgh, and I believe Jump Dev will start on Sunday and go Sunday, Monday, but we're in the process of organizing that still. So there's no details on the website. There are 2 emails that you could use to get in touch, and we've got the LinkedIn as well. And of course, there are GitHub issues and discussions. And that was the end of my talk. So thank you all for your time and attention. And if you have any questions, please go ahead.
Hi, Ivet. Thank you very much for your talk. I was wondering what made you decide to bring in your very first dependencies and whether it would, because so far I understand it was for a new solver. Does it mean you'll also add dependencies perhaps to existing code in order to make it faster, or what does it mean for the rest?
Not if we can avoid it. It wasn't really my call, but Filippo started writing the solver and thought, oh, people use BLAS, I'll just use BLAS. But we have discussed writing our own BLAS on the methods that we're using. And also I did consider writing a Metis thing just for HiGHS. So I can't promise we'll use dependencies for everything. And that's the stage we're at right now.
Thank you for a great talk. When I see solvers being compared, they are usually benchmarked by the runtime. But I have personally been involved in projects where we have very tricky optimization problems. And even the best commercial solvers sometimes fail at these tasks. So sometimes they will report that the problem is feasible, and sometimes they will not. So meaning that there is some unpredictability within the solvers. And don't know how you have considered this type of numerical, this type of solver instability, and are you achieving in this regard better than the existing solvers? And do there exist any benchmark for such very tricky problems?
Thank you. That's a great question. I'm aware of several bugs that we have had where a problem was wrongly declared infeasible when it was feasible. And I know some of these are bug related. So we have fixed some bugs. We can't say we fixed all of the bugs. A colleague of ours actually works on robust LP solution. So that's a whole area on its own. We are not specialists on robustness, but we have someone who can help us. And I'm not aware of benchmarks, but there may well be something like that. So that's something I could look into and get back to you.
Hi, thanks for the talk, and especially thanks for all the development you do. It's really valuable work, I think, for everyone, really. I'm really grateful. I was wondering, so about when you develop a new feature in the solver, when you tweak something, I can imagine that in some use cases it provides better results, in some others worse results. First, I'm wondering, is this the case? And second, if yes, how do you, when you're in the line where there's some good results here, some bad results here, how do you draw the line between saying, okay, this feature goes into the code, or it's too much of a drawback, yeah. So basically, how do you test that? Like, what kind of use cases? And then how do you draw the line, basically?
Thanks. That's a great question as well. It does happen very often with new features, especially in MIP. MIP's really sensitive to minor tweaks because of the size of the tree, can change dramatically just from something random. And we test on a set usually, and we accept features if they lead to an overall performance. So we would like to keep HiGHS a general solver, and that's why we look at overall across our test problems. But if we notice a dramatic or significant decrease in something, we like to make the options optional, like the features optional. So we allow the possibility for this to be switched off if someone's models end up taking a much longer time than before.
Hello, thank you. How the progress that you are bringing here for linear programming can be used for non-linear programming. For example, IPOP use a linearization. You still use all the libraries, MAMS, and so on. Is there a way that you can use this in IPOPs? And I have a second question. Where is the plugin for Excel if you want to target 90% of the people?
Sorry, could you repeat the second one?
Where is the plugin for Excel?
Excel? Oh, I actually think someone made a plugin for Excel. I thought I would do it some years ago, but I think it does exist. Sorry, what was the first question?
Sorry.
I can only keep one at a time.
If the progress that you are bringing here for linear programming can be used in non-linear solver.
Okay, so we are not experts in nonlinear, and that's a whole different animal. But we are looking to collaborate with Charlie Vonneray from Zeus Institute Berlin, who's working on an Argon project with Sven Leufer on this nonlinear solver called UNO. So HiGHS is integrated in UNO, and UNO have just released version 2.0, and we are looking to do more work together. And we've been talking to Charlie about QP. So that's the route we've got at the moment.
Hi, thanks for the talk. Is there a community that use HiGHS through Java? And if so, they do use Java native interface to link, or?
I think so. I remember a Java exchange at some point, but I'll need to look at more details for that. I need to check what happened to Java.
Okay. About pre-solve, I mean, usually when we compare the solvers, the pre-solve is much better in commercial solvers. And do you intend to work a lot on pre-solve, because that makes a big difference, I think, when you start with a model with much less rows and columns, of course. So do you see that that's something it's hard to get at the same level, and why is it so hard? I mean, for non-commercial solvers, what is the secret and the cooking in a pre-solve that makes this difference according to you?
Well, it's definitely hard to. I don't think we'll ever reach Gurobi's pre-solve. For instance, pre-solve is a collection of tricks, so they're a set of pre-solve rules, and you apply them or don't apply them. And we have all the basic ones and some average ones. We are missing a few that we could implement, but when we get to the more complicated ones, it starts to become tricky. So when Chi Huang Fu was working for one of the commercial solvers, he shared once with us that he spent 3 months writing a single pre-solve reduction rule. So some of them can be difficult to implement, and also pre-solve is fine, but for LP, the post-solve, and particularly the post-solve of dual values, can be tricky to get right. And then you've got to test combinations of rules and make sure they all work together. So that's one reason why pre-solve isn't so easy to advance. But we do have some scope for improvement there. So ours will likely get better, but we're never going to reach Gurobi.
So I have a tricky question for Vian. Do you feel that the HiGHS team is a sort of software company disguised in a math department, or mathematicians playing with software companies outside? Because you mentioned that it's like the relationship with the math department is a bit tricky. Because, I mean, they love you for the funds you bring, but they don't always see that you're doing research in math, right?
I guess it's both. We've got one foot in the industry and one foot in academia. And we are mathematicians, but we don't like to do so much research, I guess. So I think if we can continue to hang in the middle, that would be really great.